Okay, let's continue our discussion. So, in this video, we are going to discuss universal law of gravitation. Before that, let me do one thing here. So, in the last video, we have discussed about third law of planetary motion, and there I asked you what is the SI unit of this constant. This constant is t square by a cube. So, t is time period and a is semi-major axis. So, this is uh, time and this is length. So, the SI unit should be second square per cubic meter. Okay, and here in this case, when we are taking its magnitude 3 into 10 to the power minus 34 in this uh, particular scene or for this solar system, it is in year square per cubic meter. Okay, let's get back to the current discussion. So, universal law of gravitation. It was given by Newton. Okay, Newton's thought was that the centripetal acceleration of the moon is due to the Earth's gravity. Let me draw it first, then it will be more obvious. So, this is moon and this is the Earth, and this moon revolves around the Earth. So, there will be a centripetal force, and due to that, there will be a centripetal acceleration. So, this centripetal acceleration is AC, and this centripetal acceleration is due to the gravity of this Earth, means due to the gravitational pull. And as we know, centripetal acceleration can be given as v square divided by r. Let's say this distance is rm, so it will be rm. And now v we can write. V is speed, so speed can be given as if time taken to complete one revolution is t, and it is nearly 27.3 days, and r is this distance, and it is nearly 3.84 into 10 to the power 8 meter. So v is speed, and speed can be given as the distance covered in one complete revolution, which will be 2 pi rm, and divided by time taken to complete one revolution. So this will become 2 pi rm by t square into 1 by rm, and ultimately we will have 4 pi square rm divided by t square. And he solved it, and then he compared it with acceleration due to gravity near the Earth's surface, which is nearly 9.8 meter per square second. And he found out that this g is much more larger than this centripetal acceleration. So here, with distance, this g or this acceleration is becoming smaller and smaller. It means the gravitational force is also going to decrease with this distance. Okay. Now what he did g by ac, and it was coming nearly 3600, this ratio. And then he found out that re, which is radius of Earth squared, divided by the distance between the Earth center and the Moon center, this is also coming nearly 3600. It means g is proportional to 1 by re square, and r is the radius, so it is the distance between the surface, means a point on the surface, and center of the Earth, and rm is the distance between the Moon center and the Earth center. So centripetal acceleration is proportional to rm square, 1 by rm square. Now look, force is proportional to acceleration. So if acceleration is proportional to inverse square of distance, then force should be also proportional to inverse of the squared distance. This is what we call inverse square law. Okay. And one more thing, it was observed that having more mass will be resulting into the greater gravitational pull on the body. Means there are two bodies having two different masses, they will experience two different gravitational pulls, and the heavier the body, means the massive the body, will be feeling heavier. So if we have two bodies here, let's say one has mass m1, which is greater than mass m2, then gravitational pull on this M1 will be also greater than this one. So with these all things, Newton wrote in his work that is we know as universal law of gravitation. And the statement is any body is going to, means everybody in the universe attracts every other body with a force which is proportional, directly proportional to the product of their masses and inversely proportional to the square of the distance. So if I am explaining this thing in mathematical form, so let's say here we have a body of mass m1 and there is another body of mass m2 and distance between their centers is r. So gravitational pull, let's say mass m1 is pulling this m2 towards itself. So this force is F21. We can say there is one more force here which is equal in magnitude but opposite in direction, and this is force on body 1 due to body 2. So these two forces are equal in magnitude, and let's say the magnitude is F. So this F is directly proportional to m1 into m2 and inversely proportional to 1 by r square. And if we can combine these two, we will get m1 m2 divided by r square, or after replacing this proportionality sign with equality sign, we can write here proportionality constant g, and then we will have m1 m2 by r square, and g is known as universal gravitational constant. This is universal gravitational constant. Okay, let me write it in more elaborated way and using all the vectors notation. Here we have, let's say, z-axis, and then we have here y-axis, and we have here x-axis. And let's say we have a mass here, the first one having mass m1, and the position vector for this is, let's say, r1. And we have another body here with position vector r2, and mass of this body here is m2. Then if we can draw a vector here, if we can draw a vector here, okay, it is not coming straight, so let me do it. Okay, here, yes. So if we can draw a vector from here to here, this vector will be, this vector will be r2 minus r1, and we can write in short position of 2 with respect to 1. Okay, so if we want to know what is the force, gravitational force on body 1 due to body 2, let's say this is force on body 1 due to body 2. This gravitational force can be given as F12 equals to G m1 into m2 by r21. So this will be r21 square, and the direction of this force is along r21. So we can use here unit vector along r21, and this unit vector you know already, r21 unit vector can be given as vector r21 divided by its magnitude. So this is what unit vector. Okay, let's say here we have another body of mass m3. Here we have another body of mass m3, and its position vector is, this position vector is, okay, yes, this position vector is r3. So we can again draw a position, a displacement vector here, and this displacement vector will be, this displacement vector will be r3 minus r1, or we can write r31 vector in the same way as we have done here. So there will be gravitational pull due to this m3 on this m1, and this force, let us write F on 1 due to 3. So we can write due to M3 there will be force, and this will be G M1 M3 divided by R31 square, and then unit vector R31 here. Okay, so if there are n number of such masses other than this M1, so we will have to go for the n number of terms here, and then the net force on this body, let's say net gravitational force due to all the other masses, F1 is nothing but sum F12 plus F13 up to n terms, that is plus F1n. And then we can write it in summation form like I equals to 1 to n, and then we will have F1I vector. This is net gravitational force on the body 1. And the same argument you can carry forward to find out what is the net force on this M2 due to the other masses around it. Okay, so this is all for this particular discussion. Now we are going to take an example and try to solve. Then it will be more clear how we can use this thing. So here we have example now. Just a moment. So here we have example 7.2, and what is it saying? Three equal masses of mkg each are fixed at the vertices of an equilateral triangle ABC. So this is equilateral triangle ABC, and these masses are m, m, and m. And what is the force acting on a mass 2m placed at the centroid G of that triangle? Okay, so here is the point G, and this is 2m mass which is placed, and centroid is uh, point of intersection. Let's say if this is triangle and this is point A, and if we draw a line segment from here to the mm, opposite side, and if this intersects it into two equal parts, so this line A, let's say D, AD is median. Okay, so there are three such medians, and the point of intersection of these three medians is known as centroid. What is it given here? Okay, now moving to the next part. Okay, we have to find out force, net force. Okay, look, one thing, if you are very familiar with vector addition, you can easily say that this is a very symmetric setup. So if I'm saying that there is a force here, and this force is, let's say, F on G due to B, and there is another force here. Let's say this force is F on G due to C, and there is one more force here, F on G due to A. So you can see here, these are all at 120 degree, and they are equal in magnitude because the two masses involved in each case are the same. So here 2m, m, here 2m, here another m. So in this way, these three forces are equal in magnitude, and they are acting uh, at 120 degree with respect to each other. So net force is going to be 0. You can say it easily, but let me do it in elaborative way. So here we have three forces. One is along this F, G, A, and another is along here F, G, B, and then we have F, G, C. Okay, now this is y axis and this is z axis. Okay, you should not be confused with this one. This is y and this is x. We are taking in previous examples y and z, and then we will take x here perpendicular to these two. So we will stick to our previous notations. Okay, so this one is 30 degree. We know if this is completely 120, this will be 90, then this one will be 30 degree. Now we can write its component. Okay, so for FGC, there will be one component along this J cap, and there will be another component along minus K cap here. So there will be one component along this. So FGC can be written as FGC. Let's say if these all three forces are equal in magnitude, let's say their magnitude is F, and F we can find out. F is nothing but G M1. let's say this is M1, which is 2m. So 2m, M2. M2 is m divided by r square. R is given 1 here. So this is 2gm square. This f is. Okay. So this is also the same. Magnitude is same. Magnitude is same in each case. So FGC can be written as f cos 30 degree along j cap plus f sin 30 degree along minus k cap. In the same way, f GB can be written as, look here it has one component along minus j cap. So we can write f cos 30 degree along minus j cap plus f sin 30 degree along minus k cap. And this one is along z only. So we can write FGA equals to f along k cap. Now we can see here, if we are adding to get net force on this, this will be, we have to add, look, this is f cos 30 along j and this is f cos 30 along minus k. So these two are going to get us 0, means null vector. Now this one along the same, so these two are going to add up and then we will have 2 f and sine 30 is 1 by 2 along minus k cap. Okay. So, and here we have plus f k cap. You can see easily here, it will be 0. So, net force in this particular case is 0. Now, moving to the second part. In the second part, we have to double the mass at vertex A. So, instead of m, here we have 2m. So, m plus m here we have. Now, we can do one thing. Look, other things will be the same. Here, other things will be the same. But now the magnitude of this force is different. Instead of m here, now we have 2m. So this f prime won't be 2g m square, rather it will be g into 2m into 2m by 1 square, r is 1. So it will be twice of 2g m square. That is twice of the previous one f, which we have taken here. So the new FGA is twice of this number. So everything will be same except here we have the new F here F, let's say F prime will be, these two are going to be cancel up. This is going to add and give this much, that is F along minus K cap, but instead of F K cap here we have twice of F. So here we will have 2F along positive k cap and then ultimately it will be f, this is minus k cap, so it will be f along k cap, or f is nothing but 2g m square along k cap. So this is what for the second part, this is for the first part, this is for the second part. So that's all for this video. In the next video we will continue our discussion. Okay.